Hello, this is Shelby, and I will be covering section 10.5 and 10.6. So section 10.5 starts off with streaming data, and streaming data is data that arrives in a continuous fashion. So many application domains need to process incoming data in real time. So the textbook then gives some examples of streaming data, and the first example is stock market. So each trade made is represented by a tuple, and the trades are sent as a stream to processing systems. The next is e-commerce, and each purchase made is represented as a tuple, and the sequence of all the purchases forms a stream. Next is sensors, and sensors are vehicles, buildings, and factories, and it sends readings periodically, and this forms a stream. So next is network data, and organizations need to monitor activity on the network to detect problems and attacks on the network. Underlying data being monitored can be represented as a stream of tuples containing data observed by each monitoring point. Next is social media. Social media gets a continuous stream of messages from users. Each message in the stream of messages must be routed properly. Okay, so next is data at rest versus streaming data. So data at rest is data stored in a database. And this contrasts with streaming data because streams are unbounded, and by unbounded it means they may never end. Okay, so querying streamed data. So there are two ways to deal with streams and its unbounded nature. The first would be windows, and windows contain tuples with certain timestamps ranges or a certain number of tuples. Timestamps can help us to infer that all tuples in a particular window has been seen. Another option is to output results that are correct at a particular point in the stream, but to output updates as more tuples arrive. So with these things, we can make up methods for the querying stream data. So the first one is continuous queries, and it is incoming data streams is treated as insets to a relation. Queries in a relation are written in SQL or relational algebra, and it continually runs. Each incoming tuple may result in intersection, deletion, or updating of tuples. A positive thing about this, it can benefit in applications where users wish to view all insertions that satisfy some conditions. A negative is consumers of a query result will be flooded with a large number of updates. So the next is stream query languages. This approach, you define a query language by extending SQL or relational algebra. This separates streaming data from stored relations. This requires window operations to be applied before performing relational operations. Some streams do not require tuples that have increasing timestamps. These would then use punctuations. And punctuations are metadata tuples that state that all future tuples will have a timestamp greater than some value. So algebraic operations on streams is the next one, and it allows users to write operations that are user-defined functions that are executed on each incoming tuple. The last one is pattern matching, and in this, it defines a pattern matching language and allows users to write multiple rules, each with a pattern and action. So let's talk a little bit deeper on what windows are. So here are some window functions. So tumbling window is hourly windows. It's adjacent, it does not overlap, and it is specified by a size. Hopping windows are hourly windows that are computed every 20 minutes. They are adjacent windows that can overlap, and the width is fixed. Sliding windows have a specified size, and they are supported by SQL standard. And session windows closely model users who perform multiple operations as a part of a session. Max duration may be specified, and once it expires, the window closes. Okay, so graph databases. Graphs are important type of data, and databases need to deal with them. Graph data can be easily stored in relational database, but graph databases such as Neo4j can provide extra features. It offers specific syntax for defining node and edge relationships, support query languages that easily express path queries may be harder in SQL, provide efficient implementation for such queries, provide support for each feature such as graph visualization. Okay, parallel processing. Neo4j does not support parallel processing, but many applications need this in order to process very large graphs. There are two popular approaches for parallel processing. The first one is MapReduce and algebraic frameworks. Graphs can be stored in a parallel storage system partitioned across multiple machines. The second one is bulk synchronous processing frameworks. The graph is typically stored in memory with vertices partitioned across multiple machines. The graph does not have to be read in each iteration. That is the end.